So continuing with our study of sequences, we've seen in the previous video an example where we were looking for the limit of a sequence defined inductively. So first we're going to go over abstractly what we have done. So we are in the setting where we have a sequence defined inductively with depth 1, that is, the first term is given and an plus 1 is given as a function of an for all n. And to find the limit, of course, we would have to first justify that it is convergent. If it is indeed convergent, it might be that such a sequence is divergent, then we have to justify that. Let's assume it is convergent, then to justify convergence, very often we're going to either show that the sequence is non-decreasing and bounded above, or non-increasing and bounded below. And these properties of being non-increasing or non-decreasing and bounded either above or below are often proved by induction. We discussed how to prove things by induction in the previous video, and we're going to see more examples in this video. Once we have justified convergence, we know that a limit exists. Then, to find the limit, we know that, assuming that the function f is continuous, the limit has to be among the fixed points of the function f, again if f is continuous. Specifically, if we have a sequence defined inductively this way by n plus 1 is f of an, where f is continuous, and the sequence has limit L, then L is a fixed point, that is L equal f of L. So, you set up this equation f of L equal L, solve, you may find one or more solutions, and then you may have to decide which solution fits the property of the sequence, as we have seen in the previous example. Now, to justify convergence, we'll see that sometimes things are a little bit more complicated than seeing that the sequence is non-decreasing bounded above or non-increasing bounded below. So let's take a look at a second example where the sequence is defined inductively by the first term, which is square root of 2, and the inductive relation that to obtain an plus 1 from an, you add 2 to an and take the square root of the result. We want to know if this sequence is convergent, and if it is, we want to find the limit. Whether it is convergent and what the limit may look like is not that easy to see from the first few terms, because you start with square root of 2, then you add root 2 to this and take the square root, so you get square root of 2 plus root 2, and then you get again 2 plus a previous term, so that's 2 plus root of 2 plus root 2, and take the root of this. And so it's not that easy to see whether this will be convergent and what the limit may look like. But there are a few things we can observe. To start with, we start with square root of 2, and then 2 plus square root of 2 is 2 plus something positive, so this is greater than 2. So when I take the root, I should get something greater than root 2, in other words, greater than the preceding term. Similarly, at the next stage, we've seen that root of 2 plus root 2 should be greater than root 2, and therefore 2 plus this term should be greater than 2 plus root 2, and when we take the root on both sides, root is an increasing function, so we should preserve the relationship. That means this third term should be greater than the second one. So it looks like an induction argument, which is essentially what I was doing on the first few terms, should show us that this sequence is increasing. Yet we should properly write down the induction argument. Namely, we want to show the property P of n that an plus 1 is greater than an, and we want to show that P of n is true for all n. To do that, we check that it is true for n equal 1, and that's easy. That's what I just have observed, that root 2 is less than root of 2 plus root 2 because 2 plus root 2 is greater than 2, and because the square root function is increasing. Then we need to show that if the property is true for n, it is also true for n plus 1. So we start from the assumption that an plus 1 is greater than an, and we need to show that an plus 2 is greater than an plus 1. So if an plus 1 is greater than an, I can add 2 on both sides, and I do that because we follow the induction relation. Right? To go from an to n plus 1, I add 2 and then take the square root. So here I start from my inequality, I add 2 on both sides, and then I take the square root on both sides. Adding 2 preserves the direction of the inequality. Taking the square root preserves the direction of the inequality because the square root function is an increasing function. Therefore, I get square root of an plus 2, that's an plus 1, is less than square root of an plus 1 plus 2, and that's an plus 2. So I have the relationship at the next stage, and therefore, by induction, I have proved that my sequence is increasing. Second thing that we might want to show is that it is bounded above. Of course, we need to find a good bound for that. And you might start with the observation that square root of 2 is 1.4 something, and therefore is less than 2. And therefore, when I have 2 plus root 2, it's 2 plus something less than 2, I get something less than 4. When I plug it inside the square root, I get something less than 2 again. And similarly, if root of 2 plus root 2 is less than 2, then when I add to 2 I get something less than 4. When I plug in the square root I get again something less than 2. So it looks like an induction argument should show that this sequence is bounded above by 2. So let's try to show that properly by induction, defining the property as an less than or equal to 2, and we want to show that it's true for all n. We start with the observation that it's true when n is 1. That's easy because root 2 is less than 2. And then we want to show that if an is less than or equal to 2, so is an plus 1. And the argument is the one I just gave for the first few terms. If an is less than or equal to 2, then when I add 2 I get something less than or equal to 4, and therefore when I plug it in the square root I get something less than or equal to 2. So an plus 1 is less than or equal to 2. That means that my sequence is increasing and bounded above, and therefore convergent. So now we need to find the limit, so let's give it a name. Let's call L the limit of this sequence, and we have seen that if an plus 1 is of the form f of an, where f is a continuous function, then the limit must be a fixed point for the function. The function here is square root of 2 plus x, which is continuous, and therefore L must be equal to square root of 2 plus L. What does that mean? Well, if we square both sides, we find that L squared must be equal to 2 plus L. Putting everything on one side, we get L squared minus L minus 2 equals 0. And using the quadratic formula, or even factoring in this case, we find that L can be 2 or negative 1. And we conclude that the limit of the sequence is exactly 2 because it cannot be negative 1, because the function had first term square root of 2, which is positive, and then was increasing. The sequence was increasing starting at root 2, so it cannot take any negative value. Therefore, the only choice left for the limit is 2, and we know that there is a limit, so the limit is 2.